Thank you very much for the introduction. Thank you very much for the very interesting talk we just heard before this. I feel we are really desperately waiting for this to settle somehow, because we feel that we are right in between the cameras and the optics or the sensors with our vision system on chip, which is actually exactly what you mentioned by computational imaging, because we might be also a sink or a source for information between the customer or between the camera and the camera user and the front end, the optical front end. So that's why, once again, thank you very much for this very interesting introduction to this topic. So, well, I'm going to talk a bit more on machine vision with computational imaging with high-speed, low-latency processing in mind. I will give a short introduction on where I come from. I will show you more details on our development, on our vision system on chip, and finally present some applications we have in mind, and the conclusion how we can help you, the customer, the camera maker, or even the application people to solve your challenging vision tasks. So we've already heard some presentations from Fraunhofer, so I will not get into detail on Fraunhofer in general. Fraunhofer Institute for Integrated Circuits was founded in '85. That's the institution I represent. The Division Engineering of Adaptive Systems was founded in '92. In total, we have about 900 employees, and in Dresden, 1/9 of this workforce. And we are working basically on three main topics. The first one, which is our traditional topic, is design methodology, development and optimization of integrated circuits. And then our new focus there is the reliability and functional safety of this design. The second topic we are working on is efficient electronics. Basically, it's sensor electronics, integration of sensors into whole processing systems, which is not just the electrical implementation or an electrical integration, but also the system integration in terms of 3D integration, and last but not least, the sensor, optical sensor technology. And the last topic is distributed data processing, because data we generate with the sensors somehow have to be processed in a feasible manner, and there we concentrate on industrial data analysis, wireless network automation, analysis of data again, and energy management, which is a good application for methods we use for data analysis in general. So this is something you most probably all know. That's a generic approach on vision, on image processing. We usually use illumination as good as necessary, and cameras as good as necessary again, depending on what we are looking for, on what defects or whatever we are trying to capture. And then the images are read out into the camera, and then from the camera to a processing unit, the raw images are processed there at a speed feasible for the application. In this case, we are talking about 2 seconds time per processing step. And then most probably we have a feedback to the process, to the in this case transport process, to use the results we just generated for a certain action. What happens if this does not use just if we are operating not in the second range but in the milli or microsecond range? Then it gets really tough, especially if we are relying on a feedback within this range, on a latency well below millisecond range. Then it's getting much more difficult, and there are quite some approaches to this. I will present our approach, how we designed or how we specified what we are doing with our vision system on chip. At first, the question of resolution. It's always the hunt for the better picture, the better resolution, low level levels and so on. But we are talking about high speed. That means exposure in the microsecond range. Then we have to cope somehow with a limited number of photons. And that's why the photon shot noise limitation kicks in heavily, and we decided to use a resolution which is feasible for this kind of high-speed imaging. So that's the next thing. We just heard about this. I've just wrote it down in a little different manner. That's exactly what we focus on. Don't compare the result from the image itself, but compare the result of the measurement process. So if we do sheet of light, we compare the quality of the 3D data. So I used pixel peeping, which is, well, okay, it's not a very technical term, but that's exactly what we don't want to do in general. The next thing, frame rate, the throughput. We are working in processing, not just capturing the image and then offloading it to the PC, but we want to have a low latency feedback, and therefore the I/O bandwidth is a limiting factor usually. So the chain from image capture, processing, and output of measurement results has to be as efficient as possible. And there, the parallelism is driven to an extent where we can still cope with the data we output of the process, the measurement process. That means pixel parallel is fine if you really can get the pixel data, the results of your processing out of the focal plane. But in our case, running at 10,000s of frame per second, it's quite difficult to grab all the data. That's why column parallel processing in our case is completely sufficient. That's why don't generate data you can't process. The next is power limitation. We do imaging, we don't do heating. We don't want to heat up the focal plane. That's why if we generate too much power or too much heat in the sensor, that of course decreases the image quality. That's why we do processing on the image sensor, but we have to limit the clock rate of the whole processing units to where it's feasible or it's necessary for our processing task. That's why every of the units we use is somehow clock limited to the actual processing task. The other question is asynchronous design, where it's beneficial. There can be a lot of good opportunities based on asynchronous processing, and this is something we heavily use for certain things on the sensor. And last but not least, cost limitation. We know that we will, at the beginning, not be able to bring millions of sensors to the market. We're doing machine vision, and we have to at first convince the customer. That's why one very important question is, even for low volume, how expensive the whole design is. That's why it's, at least for us, it's very difficult to get the performance from the architecture or from the design itself more than just using the technically forefront integration technology. That's why software-defined function, in our case, software-defined smart camera is the device at the end we are targeting it. So now some little information of the basic VSOC we have developed. You can see it at the entrance. I have prepared some demonstration on this. It basically consists of sensor metrics with, in this case, 1 megapixel, 8.75 pixel pitch, and linear logarithmic characteristics, especially for high dynamic scenes where if we grab or if we capture gradient information, then we of course don't want to see saturated images. Then this is completely freely in software controlled by a line control processor. ASIP stands for Application Specific Instruction Set Processor. So we have a processor that runs at 100 megahertz, filling all these memories and all these shifting units with data to control the region of interest or the global rolling shutter mode or the filtering, whatever is possible by this setup. The next thing is we have column parallel processing units, 1024, one per column. And these are again controlled with a second ASIP to do a column parallel processing. The first part, of course, is the digital analog to digital conversion. This is done at software level 2. That means we can do a binarization, but we can also do an 8 or 10-bit A to D conversion. And to have the opportunity to communicate internally and externally, there is a global control processor which has a couple of different interfaces, high-speed parallel interface in this version, and SPI, and very important general purpose I/O. This is something where we can, with serial protocols or with high-speed protocols, communicate not just with our camera system, but also we could operate the external lens or illumination with a very, very closed loop. We are talking here about 100 megahertz frequency at which this processor run, and this processor can operate that general purpose I/Os. So then, of course, infrastructure is always needed, and besides of the hardware, we need a lot of software. That means compiler, assembler. The system is programmed in Python natively with embedded assembler, and of course, algorithms and implementations for a number of processing tasks. I can show you some of them. I have an implementation of histogram of oriented gradients, and I will get a bit more into detail on this later in my presentation. So now I said we are not just presenting what we already have in a camera, in a demonstrator. We also are working towards new features, and one of these very special features is the operation of data with sparse pixel information. The first is how you would read out an image sensor for a sheet of light. Well, you go through the matrix, you read it out line by line, you digitize all the interesting and non-interesting pixels, and you end up with a readout time, number of lines, times columns, times output operation. Well, this is possible, this helps to a certain extent, but this also puts the limitation to the interface speed. We are, as you already heard, targeting on low latency operation. That's why we introduced a new possibility to improve that by introducing a cache memory. You know this from digital processing, where it's state of the art for many years, tenth of years. But in our case, we use this to storage intermediate analog results. How to operate with this new feature? Well, we can read out pixels line by line in a fast scanning mode, and then look at the data we just grab in the based on binarized data in our processing elements, and behind the reading of the data, we can just storage or we can just cache the analog data. And then we decide, are the data we have cached in the past interesting or not? And if they are interesting, column-wise, the processing unit can decide whether to keep the data or to drop that. And afterwards, we can do a high precision readout. We don't not storage only the data, the analog data, but also digital information combined with this data, like the line number for the first occurrence of an interesting feature, and so on. And by this, we can increase the speed of the whole readout and the whole processing tremendously, depending on the quality of the data and on the pre-filtering of the data. So this is what so now, this can be done line-wise, but we can also do the same thing in column. Well, let's say we're looking at sparse pixel values. That can be a gray value, but it can be also an edge we are looking for, depending on what features we are looking in the focal plane. And usually you just read out the result in the processing elements one by one. And if they are 1024 and we are looking for one or two of these values, maybe two addresses of the coordinates and the gray value, then we're just waiting for a whole bunch of uninteresting data to read out. So this is the normal approach. And we decided this is not sufficient for high speed and introduced an asynchronous readout mode, which just feeds all the data. So the processing elements just mark their data as interesting. This can be done in software. And then the readout is done in an asynchronous manner that only the interesting data appear at the exit, at the output. And by this, especially for operations like white light interferometry, we can increase the speed, especially if there are very sparse information in the focal plane. So how does that look like in the first demonstrator we implemented on this? We have a sensor with the features I just introduced to you, and other very important features we need is communication between the units. So we introduced a network on chip, and this is basically how we showed the different possible optimization ways. So what can you take home from this introduction or from this information? So some interesting application for this VSOC in general or traditional application is the processing of simple blobs. You can see that in laser welding, for instance, you want to see the center of gravity and the shape of this blob, and you want to just track it in order to get feedback information or control information for the laser control, focus, or speed and power. And this can be done at a latency of 1 frame and at time of 100 microseconds and much below, depending on how good or how the blob travels on the focal plane, how far it can travel from one frame to another. So the next interesting application I have with me to demonstrate is a feature on-chip feature extraction. One application is presence detection with privacy by design. So we don't want to output grayscale images, but we want to output features that can be used to classify the image contents. One very good and very powerful feature and well-known is a histogram of oriented gradients, which contains not just the calculation of a gradient, but also the direction of the gradient based on a quadratic algorithm. And when we can calculate this on the VSOC at 40 to even 50 hertz with the power consumption in the range of 200 milliwatts on the sensor. Comparing, we did a comparison, we used OpenCV and calculated the same on the same resolution on a Core i7 with OpenCV to give a baseline. And for the normal CPU without GPU, to be honest, it takes like it can do 7 frames per second. So what you see here is you see a massive reduction of power consumption because we do calculation on the edge at directly close to the data. We don't have to transfer all the data, and we don't have to do this in a chain. And the other very important thing is we can do processing on the sensor, and we don't have to publish data, grayscale data to the external. So what you see here is not just the HOG, but the gray level or the colored output of the gradient, the angle and the value. So that was too fast. Next, I said I have shown to you our approach to increase the speed for sheet of light. This is once again how this operation is done. At the end, you end up either with maximum 32 lines in the cache out of 1,000 lines and can do the off-chip center of gravity or whatever you want to do. The other option is to do the same on-chip in the processing elements. With 100 megahertz, there is plenty of time to calculate this if we are running at, for instance, 10 kilohertz of above. The good news is the next design we are working on will also have 2,000 columns and 1,000 lines. And we are relatively confident, although we have no measurement so far, that we can operate this at a couple of hundred milliwatts. And what you get out of the sensor, you don't get just grayscale images or gray level data, even though they are just very limited number, but you can get a real profile out of the interface of the sensor. You can build a sheet of light sensors at a very compact way and at very low power consumption to be able to implement this really at the edge or at the machine you want to do that. So last but not least, I showed you the opportunity to do white light interferometry. This is also just in software, and we are confident simulations show that we can run this readout, which does a differentiation of consecutive images at up to about 1.5 kilohertz, and then of course, depending on the number of data you read out, you are limited there. Of course, the bandwidth is always an issue here. But if we get the data out of the interface, and I think the interference modulation between 5 and 10% is completely okay to get all the data, we can operate in the kilohertz range. So, as a conclusion, we have developed an vision system on chip architecture with essential customer needs in mind. It has some unique features, especially with regard to low latency and high processing speed. It's extremely flexible for a high variety of special applications due to the fact that it's completely software programmable. And now we can start to realize real applications that are beneficial from our VSOC approach and enable our customers to bring this technology to their products. So very important, of course, this R&D has been funded in some R&D projects. 2 of them are given here. And very important for you, most probably, is how can you benefit from this development? How can you, maybe as a camera maker or as an industrial measurement system maker, benefit from this? Well, this can be used, this device, or even the final camera. We are not a camera maker, so we are teaming with camera makers to implement whole systems, camera systems based on our VSOC. This can be used for quality improvement and, very importantly, for optical process control. You can implement such a device in real measurement and production process with this close feedback. And we can do customer-specific smart camera system. Even the customer can build software. I mean, writing software in Python is one thing. Of course, if you want to have it really highly optimized, then assembler is the way. But at least this is possible. We are not talking about completely closed system. So this is a very important fact that we present here. The sensor module is one option to implement just the sensor module, to integrate it with software already, or to optimize, in this case, the total system costs, because it's not just the system itself, but it's also the bill of material for the total system that we have in mind when we implemented all that internal references and everything in that device, so that it can be used, it can be integrated very fast into new designs. Thank you.